Then the customer said, yeah, 3,000 of my 5,000 trees actually said he's a bad customer. So what are these trees saying something, and why should I trust it? So there was absolutely no common point, common ground. So that's when they asked us, hey, black box models are not acceptable in this problem, in identifying which customers are good. You just don't come and tell me you did some cool math and hence this guy is a bad customer. And I can't believe that. Give me reasons for that. And how do we get that? And one interesting, very interesting approach that we found very successful and several good practitioners follow is, given the original data, yes, it looks odd like this. It looks non-linear. It looks incomprehensible. Can I find some other set of attributes? Can I identify other features about this data through which, if I look, I get this nice separation? So essentially think of it as in the given angle with the given attributes, it's all messed up, it's all overlapping and all. Can I actually create a bunch of new attributes, new features? This is called feature engineering, where actually the models become simpler, the data gets nicely spaced out. And there is a lot of work that is going on today with respect to engineering features. And this engineering features, again, is a joint activity. There are some machine learning techniques that automatically help you engineer. But the domain expertise and brainstorming, and that's what, in my opinion, in my experience, when we first get a project, we look at attributes and we say how many new attributes we can create. We spend at least a week just doubling up the attributes. In this case, what did we say? They gave us around 50 attributes. One of them is what game they were playing. Then we asked the question, did they have a favorite game? What do we mean? Is the family playing the same game most of the times, or is it playing multiple games? If it had a favorite game, then is the behavior different? So we inferred that from the existing data that was not there. Secondly, there may be two families with two kids. Family one's kids are 8 and 6 years, family two's kids are 18 and 6 years. Do they behave differently? 8 and 6 and 18 and 6. The domain expert, the business user, felt there would be a lot of difference. Interestingly, we didn't see any difference in the behavior. One of the learnings we had was the is the age of the eldest one, he is playing to the age of the younger one. So 18-year-old is behaving like a 6-year-old. It's the 6-year that decides. So the youngest kid is the thing. Third one, when did they, we have the point of sale data. When did they make the first sale? January or February? Does it matter? As we'll see, all these mattered actually. So we spent a couple of weeks just creating these new attributes with the hope that maybe we'll find some angles where the business user can find value and in the predictions. And then I'll show you some of the predictions that we were able to, some of the insights that we were able to get. Here in this graph, please ignore the green for the time being. The red are those that played a single game. They had a favorite game in the first 4 weeks, first month. So these guys played a single game in the first 4 months after purchase. These guys, blue guys, played multiple games in the first 4 weeks of the purchase. And the y-axis is the revenue they gave in 2 years, after 2 years. So when they bought the product, in the first 4 weeks, these guys played a single game, these guys played multiple games, and this is the revenue I got in the next 2 years of their span, the lifetime value. Lifetime value here we defined as 2 years. And we were able to show that the average revenues of the people who play multiple games, it's a bit difficult to read, this is around 25.5, this is 7.5. Average revenue that you can expect in 2 years from the guys who play multiple games in the first month is 3 times more than the average revenue that you can expect from people who play a single game in the first 4 weeks. Now, this is something, when we actually made this insight available, the marketing team just was, for 10 minutes, there was so much of noise and discussion in the room. It's a great thing to happen to a data scientist. So they said, yeah, what is wrong with it, most likely, probably we have to give more games along with our first purchase. We are currently giving 3 games with the hardware. Maybe we should give 10 games. We should encourage them to play as many more games as we can, so that they will spend more time. Again, this is the amount of time spent. This is the number of games. This is the time spent. So these guys spent, people who played a single game on 2-year span, spent a lot less time. This is around 1900 and this is around 14,000. So they spent minutes, spent a lot less time compared to the people who played multiple games. So those who played a single game spent a lot less time in 2 years compared to those who played multiple games. Now, this is not even a model. This is the entire data. I am just plotting it, that's all. No model, no mathematics, just description of existing behavior. And that was a very useful thing. What was another extremely interesting insight for us was, they said, hey, don't worry about any sales that happen between February and November, because all our sales are, they call them cohorts. Our December, January cohort is so much more important than our Feb to November cohort. And this sort of proves that, this is the sales they got in January, this is the sales they got in December, and more or less insignificant. And it's, they said it's the Christmas time, it's a New Year, Christmas, people buy, so just worry about it. This is where practice of data science actually helps. While we are actively working with the business user, we train ourselves not to listen to them too seriously. We are respectful because they bring in insights that we don't have, but we don't trust, because unless the data tells something, we will not be convinced. We are trained to listen to the data. If we are true to our profession, we only listen to the data, validate what we learned from the business user. If there is a conflict, we trust the data more. If there is no conflict, yeah, great. So what we did is, okay, they are believing the January and December cohorts to be most important. Let us see how much of revenue that we got from them after the first sale. So yes, there are this many first sales that are happening, but then they are buying games after the first sale, right? So these are the months again where the first sale was made in January and revenue that we got from all the sales that happened afterwards. Average revenue that I got from all the sales. And as you can see, actually January and December are the worst months for cross-sell and upsell. If the person bought a product in January or December, there is a much less likelihood that they will buy anything else from me. This y-axis here is the revenue that I got, and these are the lowest points. Whereas somewhere in summer, if the first purchase was made somewhere in 7th month, July, actually I'm getting a lot of upsell money from this customer. And when we said this, they went back and said, yeah, great. This makes sense because January and December, people are on a gift buying spree. They just pick a product and just give it. They're not careful about having it used. Whereas in July, or August, if a parent is spending whatever, $50 on a gift, they're thinking carefully. They had 7 other options, which one to buy, and they bought this specific one. And hence they're likely to make the kids use it as much, and then are leading to follow-up sales. So the very crucial lesson, and I said that already, it is not only sufficient to be patient when the data scientists are understanding or processing the data. Actively get involved with them and help them build the data better. Massage it, create features. How many new features you created is a question that you should ask. Whether we internal data team or you engage a soothsayer or whoever. have them come back to you and say, this is the amount of work that I did on building your data, and now I'll go to the models. And this is not just our understanding, this is experimented, and some of the greatest minds in data science spent a lot of time on finally convincing themselves that great models on simple data almost always lose to simple models on great data. Okay, so as you can see, I didn't even build a model in that case. I mean, we did, and we ended up building a nice model and going back to them and say, yeah, this particular customer for this reason gives you $50 to $75. But even I didn't have to go there. Just creating this new data attributes and looking at the data from those attributes was a great result. And at times it is interesting that it is intuition crushing, like the example I show. Business user with 5 years of experience thought December data is all that we needed to look at. But cross-sell, it's better to look at November data or whatever, July data. Similarly, the business user thought two families with 8 and 18 and 8 and 10 behave very differently. But we found, no, it didn't matter. As long as the youngest kid is of same age, families are behaving the same way. So things like that are intuition crushing, and the data scientists can give you a lot of experience in doing that. Okay, so this is where I want to take the first logical break, a 15-minute, and then when you come back, what I want to talk about is problems where really advanced mathematics is inevitable, and show you how in such cases data scientists actually go about solving the problem. So next time you see a black box model, you will be a bit more receptive. We'll talk about, so far we showed problems where I can avoid those complex models and actually get an output that the business user likes, but then there are some problems where I cannot. And you need to then understand what exactly we do and take it from there. Okay. I will talk about one more interesting lesson that I recently learned, again with a use case. And the last part of the session, I want to talk about two important phenomenon that business users will need to understand. One is, what is this big data about? Everyone talks about big data all the time. So I just want to give you a feel of what is involved there, what do we do, so that you can sort of get an intuitive feel of what is happening. The last one, my experiences in building a data science team. So the question is, who is a data scientist, or what does a data scientist mean? What can we expect? We will have to figure out, I'll share with you where I think a typical HR process is going wrong, and how you should probably bridge, what skill sets you should use, what infrastructure should be used, etc. So that's how this session will be. So interestingly, you end up using more complicated mathematics for doing things that humans can do very easily. So recognizing a picture, face recognition, is, tomorrow if you see me somewhere in a mall in Detroit, probably you'll be able to immediately connect, yeah, this is the guy that gave the seminar yesterday. How are you doing that? What factors are you taking into account to actually recognize a face?
Recent memory.
Recent memory of what? So you are seeing some pixels, or are you seeing, what are you seeing? It's a philosophical question, right? And people thought about it a lot, and for 30 years people actually went in the direction that I talked so far. They actually computed various features, the distance between eyes, the length of the nose, the width of the mouth, whatever they are. They used to give computers those insights, those inputs. They take a picture, they measure all this. But then there is another group that is crying and cringing, I am sure human brain doesn't do this. I am sure I don't measure the distance between eyes of a person to recognize that person. Because I don't even have an approximate idea of what it is. 2 inches, 3 inches, 4 inches, I don't know. So there is some other way in which this entire brain functioning is happening. So computer vision is one second thing, equally important thing, understanding text. How are we, and I'll show you a few examples. This is a statement I found in Twitter. My in-laws are as sweet as Nazis. And, right? We all know that his in-laws are not sweet. How do I let a computer know that? How much of Second World War I have to teach the system for it to know that this is sarcastic? This is actually not a compliment. Then this is my favorite I got from Washington Times. FBI is tracking terrorists with bombs. Who has the bombs here? FBI or the terrorists? We know FBI probably is not throwing bombs at people and tracking them, right? Most likely the terrorists had the bombs. How will any, to the best of my knowledge, the most cutting edge computing systems will give a 50% probability to FBI or terrorists. Who has the bomb, if I ask? 50% of the times they think it is the terrorist who has, it's the FBI who has the bombs. They are tracking the terrorists with bombs. And this one, who am I talking about? Yeah, it could be a gangster who has his dinner and then while leaving he just shoots the guest and walks out. Or if I remove the comma, and many a times, none of us are, the ability to punctuate things, sentences is only going down. If I say he eats, shoots and leaves, maybe I'm talking about a deer. Shoots as in bamboo shoots and leaves as in tree leaves. A deer eats, shoots and leaves.
It's in English. That's a book from. There's an actual book with that title.
Oh, yeah.
Okay, and it talks about punctuation.
Yeah.
And the actual example was a panda bear.
Exactly. Yeah, exactly. So how do I build a computing system that actually understands, based on punctuations and based on these complexities, what exactly I'm referring to? These are nonlinear. What do I mean by nonlinear? A small comma changes the context completely. That is nonlinear. Linear is change in input changes the output in the same ratio, same proportion. Nonlinear is change in a small change in input leads to a huge change in output. I'm sure you all heard of that butterfly flapping its wings leads to a tsunami. That is what we are looking at. So in such cases, one has to deal with, when I'm trying to simulate brains, we need to deal with nonlinearity. And how much ever effort that we put in getting simple, understandable models, we won't be able to solve it. So when your data scientist is pushed to get into a nonlinear model, you just should have an understanding of what he or she is doing there. So let me spend a couple of minutes on a couple of examples on showing how we go about building nonlinear models. So let me take again a very simple data. There are some red, then green, and then red. Linear model in its most general thing is a line. Can I draw a line anywhere in this picture such that all greens are one side and all reds are one side? If I draw my line here, there are greens, but then there are reds. If I draw my line here, there are greens on this side, but then there are a few reds. So we cannot draw a line that splits the reds and greens cleanly. So the only, one of the many approaches that we have is probably draw a circle. Draw a circle. Now I can say within the circle everything is green and above the circle everything is red outside the circle. So essentially, but this is nonlinear. And it's easy, simple nonlinearity, but still nonlinearity. There is a very interesting intuition somewhere around mid-90s, a brilliant scientist came up with. He said, you know what? If I actually square this every point, instead of just taking that value, if I just square it, if I take to a higher dimension, now the squares, obviously, you get a cup like this, and I can actually build a line that has all greens on one side and all reds on another side. A very, very interesting intuition is data that looks clumsy and overlapping and non-linear. If I actually somehow can take it, square it, cube it, there is elegant mathematics that happens here, and many people believe that this is one of the most mathematically beautiful inventions in machine learning data science in the past decade or two. The idea is as simple as this. Data may be clumsy in the space that you are looking at. Just square it, cube it, infinite times you rise the power, you get to a space where everything is neatly linearly separated. Build a model there, a linear model, whatever, logistic regression or decision tree, whatever, and then pull it back to the, project it back to the original space. It becomes automatically clumsy. So data scientist doesn't build a nonlinear model. He or she takes the data to these high dimensions where it gets linear, builds a linear model, projects it back to a lower dimensional space. By the way, this is called support vector machines, one of the most advanced machine learning data science techniques that we practice. Whenever your engineers are stuck with nonlinear data, probably this is the way they should go about solving it. There is another equally elegant and competing way of solving the same problem, which is, I just told you, all nonlinearities are not equally scary. This is nonlinear, but it's only a cup, this is called quadratic equation. Yeah, it's okay. Instead of y is equal to x, it's y is equal to x square. So it's not scarily nonlinear. So there is some point where business users find it scary, non-linear, and scary as in inexplicable things. But there is some amount of non-linearity that can be probably lived with, managed and handled. Now, another approach of building a heavily nonlinear model, however nonlinear the overall thing may be, I can write it as combination of these simple non-scary nonlinearities. This is a cup. Can you see a cup here? Now this is a line. I go lines, then I'll have a cup, line, cup. I can combine these easily understandable cups and lines to get a extremely nonlinear shape. But internally, at a fundamental core level, they are very simple, easy to manage nonlinearities. This is another approach that is sort of shaking the world nowadays. It's called deep learning. So you take all your lean inputs, and then at every point you just add a cup or a line, just a bit of nonlinearity. But then you keep building and building so much of nonlinearity that by the time you go here, you have an extremely complex field. I don't expect, and this is not the purpose of this session, to actually teach the mathematics that determine deep learning or support vector machines, but I just want you to know that when your teams are saying they are building a black box or a nonlinear model, actually what they are doing is not some weird mathematical magic. It's a fairly simple common sense with a bit of equations here and there. By the way, this particular technique is nowadays, in 2013, MIT every year publishes the most disruptive breakthrough technologies. And in 2013, the top 10 they published, the number 1 technology was deep learning. They believe it is disruptive. And it is truly improving the benchmarks that are set in machine learning dramatically. So if previous techniques were giving 70% accuracy, this is giving like 90%. It's shaking the world. So it's wonderful. But unfortunately, this has as much a fan base as a hate club. That's because instead of talking about this as a very simple and elegant way to build nonlinear problems, the practitioners, quite a few of them, say this is the way human brain works. And for the past 60 years, there is a group of people who are building these models that claim they are cracking how human brain works, and there is a hate club of philosophers, psychologists, practitioners, medical practitioners who believe, who say you don't know what you are talking about, man. This is so simple. Human brain is so much more complicated. So there's a fascinating struggle. In 1950s, they actually figured out the math to solve just this part. Just this part. And I have it somewhere where the press coverage, if you see, we figured out finally how brain works. They called it prodigy. And then they said, great, this is how human brain works. 1950 to 1960, any paper, any research conference, people only talked about prodigy. And then 1960, someone came out and said, you know what, brain is more complicated than this. And they mathematically proved. The other team just went with a vengeance and just said, close this, this is not brain, you have been misleading us. And 1960s and 1970s, this died. And people were scared to say that they were working on neural nets. That's what this is. Then 1980s, they figured out how to solve this problem. Just one more layer, how to add. And then the neural net guys came, now we know how brain works. We are, this is what brain is. And then these guys, the psychologists went back quiet. Everyone was doing neural nets all over the place. In 1994, a group of economists from Harvard, I don't know where they're from, they built a model to predict stock behavior, and they got a Nobel Prize. Even more dangerous than that, they got $3 billion in investments to actually spend in markets. 2 years from then, they declared bankruptcy. And then they realized, oh, after all, this is not human brain then. Maybe it's more complex. Again, the hate club just rose and fought with vengeance, and they, neural net community went quiet. Now, 2005, they invented how to build a much larger network. They say, yeah, now we know how brain works. This is how brain works. But in reality, human brain probably has 6 billion or some billions of layers like this. Does it work like that? Is it a snapshot? I don't want to get into that discussion. Because as long as you take it as a nice way to do nonlinear problems, it is fine. I think it's less controversial. This is powerful. As long, the moment you start saying this is how brain works, I think it gets really, controversial. So an interesting work that Google did recently is they gave a picture from YouTube, pixel value of each picture, pixel value, and then automatically by building nonlinearity layer by layer, by the time it came to this red dot, the system was able to group all pictures that had cats in them. They didn't tell what a cat was. The system didn't know. They just gave the pixel. They didn't give the distance between eyes or anything like that. They just gave pixels. Let the system learn, build nonlinearity step by step, step by step. By the time it came here, it was actually able to know this is a cat. So that's a very popular paper published, I think, 2 years back called Google Cat Paper. But we can do more interesting things than finding cats. That itself has a lot of value, I'm sure, to YouTube. But from a business point of view, this is a phenomenal tool to create features. In my personal experience, when I go to a business, they give me 100 attributes. I'm unable to get a good model. Then I just non-linearly build features, and then some of these features that I identify that the business user didn't know,